Welcome everybody to the final talk of today, Monday. It has been a pleasure, Yara, you're ready. Anyways, this afternoon, this final part, we're going to talk about experimental uncertainties broadly, and we're going to focus on the design of experiments, taking into account uncertainties and Bayesian approaches. But we're also going to talk about how the uncertainties on the experiment actually make all their way, not necessarily know the details, but all their way to a final prediction that is what I, as a theorist, take as an error bar. Joining me is Rahul, another excellent and outstanding PhD student, now not from Ohio, but from here at MSU. We are extremely blessed to have such a fantastic team of students and postdocs and faculty working with us in the organizer team. So Rahul is going to tell you a little bit about the uncertainties in the experiment. And before we start, I want to highlight something pretty cool. Well, at least I think that it is cool. I usually put hats on the characters that come with me for my presentation to represent friends and collaborators. And for me, I have my books, that is my signature hat. And for every time that I put a theorist, a generalized theorist, I put a coffee cup. That's their hat. Rahul here, my friend, is both a theorist and experimentalist. He works in both fronts at the same time because he gets very bored very easily. So I was thinking, what should I put for his hat? And then I thought, a coffee cup with two wrenches on it. Where in the internet am I going to find something so specific? So I couldn't find that anywhere. And I asked one of these image generators, AI, can you make me a cartoonish version of a coffee cup with an Allen wrench on it? And this is what it came up with in like 25 seconds. And it's amazing. Imagine when we can do this with nuclear models, we will all be out of a job. Anyways, I'm going to take the first part. So Rahul,
sure.
You're free to sit down, but I will call you when we talk about the experiment. So this is the outline. I'm going to guide you through a first example that was actually my first encounter with both Bayesian anything and experimental design. We're going to try from that example, because it's a good example, but I know it very well. That's why I'm using that one. We're going to try to identify what are the players that play a role in the type of decisions that you need to make in here. By the way, if you thought that after this talk you were going to walk out of that door being experts in experimental design and you can call all your collaborators and say that now you can be in charge of the design of all the experiments available, of course not. This is what I want you to take out of this is what are the questions, the type of things we usually need to think when we're doing this type of approaches. And it's a very difficult problem, the same as the Bayesian model mixing that Alexandra was mentioning. We're going to go through what should be the perfect example of experimental design, and we're going to realize that it's impossible to do. And then we're going to do the hands-on challenges, and you will have to do impossible things in the last part. Throughout this presentation, as I mentioned in the previous one, please ask questions. I will be very happy to make it interactive, both for me and for Rahul with his special artificial intelligence hat. Okay, so first example. I was sitting in Florida, arrived, have been there for a year, Florida in Tallahassee, Florida State University. And my mentor and advisor at the time, Jorge Pikanovich, he came to me, that is his hat, because he really likes football. And he gave me the following challenge, the following problem. We are trying to measure the density of nuclear matter. So in an experiment, that's how a theorist thinks things work. I have a particle going pew, pew, and I shoot some particles, in this case electrons. They interact with your target, that it could be the nucleus of lead or calcium-40, for example, or calcium-48. The electrons deviate some amount of their trajectory. You measure that. From that, you can reconstruct a cross-section that then you can make into a form factor, that then you can make into a density, this row here, that actually tells you how much stuff you have as you go from the center of the nucleus away through the edges. And the way that that curve behaves gives you some information about structure. Remember that we were talking about structure in the first lecture. If I want to measure the charge distribution of protons, that is relatively easy to do. But if I want to make the charge distribution for neutrons, that is extremely expensive and difficult. And that's part of the analogy that I was saying, that half of the screen is broken because detecting neutrons is like really, really hard. Nevertheless, we really want to measure that, because if we were to understand some properties of the difference in distribution between the protons and the neutrons in a nucleus, and in here I have this cartoon that shows the neutron spin, that is this quantity, the difference in radii of these two things, we will understand important information that relates not only to nuclear physics, but to astrophysics and neutron stars. So the situation that Jorge told me is like, this is a form factor of lead-208, for example, and we have measured one point on this curve. If I want to measure another location, where should I measure? And my experimental friend, she says, this is a very, very expensive experiment. Remember, the screen is broken, so it's really hard to measure this thing. What will you do? If you're Pablito sitting there in 2016, just not knowing what the heck to do and looking at this graph, where will you choose if I give you all of these options to put a second measure? Any ideas? There, where is there? Yes, thank you, Edgar. Any other ideas beyond there?
Region with our highest uncertainty values.
That actually seems like a very good idea. You know, I'm going to grab my model, I'm going to make some uncertainty bands or credible intervals that now we're experts on how to do. And I'm just going to select, I'm going to put the next place where my model is most uncertain. Maybe, and that is a maybe, but maybe that will inform my model the most. It's kind of similar to when you're training a neural network. If you have played with this and you're trying to like, where are you not getting things correctly? Like you are saying that this cat is actually a pickle. I'm going to hit you and modify your weights until you fix this one that was the most difficult problem that you were. So that is the idea. And that's what I said. After months of thinking, you came up with it much, much faster than I did. And some friends from the statistics department came up with a similar, much more robust reasoning, but basically the same idea. And we said, okay, I'm going to calculate the variability of my model, this sigma, and I'm just going to say, I'm going to add the new location, wherever that is sigma. And that is this paper, that is my first paper with my advisor, Jorge, and our two friends, including Dr. Chicken. And I always found that super funny. Anyway, I have my form factor, F, that depends, yeah, if you Google him, you will see in his webpage, he has like pictures of chickens and all his grad students are like that eggs, and it's super. Form factor. My form factor depends on my parameters alpha. Remember the notation that we were using at the start. And in this case, two parameters, doesn't matter what they are. But obtaining these parameters, I can reconstruct the density, which is what we want. Remember, we want to understand the distributions of protons and neutrons. And to reconstruct that, what we eventually end up having is a posterior distribution that we did through Metropolis casting. That's why you have so many points in here. And we can say, hey, my parameters are more or less around here. And I am trying to find the locations that I need to measure such that this posterior distribution is very constrained. And the final thing that we were interested in this case is the distribution of the radius of the nucleus. Remember, that's what we were after. All good, all works out. Let's try to identify what were the players in all of this discussion. The first player was the experimental data and errors. The existing one, that is this one here, that was very expensive, and all the availables that I could have. That I could just discretize the thing and put it on a grid and say I'm going to optimize over these things. The second was the theory model. In here I have the equation for how this looks as a function of my parameters. The details don't matter. I just want to show it to you, but the equation itself is not important. And the third thing is the quantity of interest, the thing that I'm after. I'm after the radius. I could be after other things, but in this case, I'm after the radius. All of these things, the existing, the possible, the theory models with an S, because in this case, we actually had two. We were not mixing them. We were doing something more simple, but in principle, you could mix them, as Alexander was pointing out. And the quantity of interest, you put all of that in a black box. You call that black box J, because that is a traditional thing that we do to call utility functions, and you try to optimize that utility function. And that is your optimal design. That is how you select, in that case, where and how you're going to measure. The how, by the way, refers to how much error bar you need to put to this. So in that paper, identifying the players, you already know what this is. My models were this F and a second one that I haven't mentioned in detail. And actually, we didn't put our quantity of interest in the black box on that variability idea. The idea of variability, I was not specifying what I was interested in. I was just saying, where's my model most uncertain? Boom, I'm going to measure it there. I might be interested in the radius, but I didn't have to think that through. But that is an option. So that's why I want to identify it as one of the players that you could. And by minimizing that part, the utility function that was the variability, I could go and measure my second value of the momentum transfer. Now, in principle, you could say, well, what if we change our utility function? Instead of going and finding the variability, I'm going to make this animation that was extremely expensive for me to make a couple of days ago at night. And in here, I'm showing you the posterior that you will get if you measure in one single location. By the way, you will realize that this gray posterior is bound, even though that I'm measuring in a single location. Do you know how that is possible? How can I obtain a finite distribution of parameters if for two parameters just measuring one location? This is a nice lesson for you all. Anybody has any ideas?
You need extra confidence in the line result. They stay outside. Just a matter of probability.
True, but in principle, I could have an infinite amount of parameters that are consistent with this measurement. And in this case, the answer is because I have priors. So the priors act in some sense, if you want to think of that as a regularizer, that is also pushing the parameters to whatever I believe that I have. So with only one observation that is here in blue, I obtain this posterior. With two, this is showing how much information gain under this metric you're getting as you move your location for a fixed value of the errors. I could say, no, I don't want a posterior, I don't want a posterior in the parameters. The parameters are meaningless. What I want is the quantity that I'm after, which is the radius. And then I can make the same plot. And you see that right around the second diffraction minimum, this posterior has the smallest uncertainty, and that could be a way of selecting where I want to measure. But in this case, it's taking into account the actual thing that I'm after. The final thing that you could change in this very relatively simple example is saying, okay, suppose that I selected two locations and I can talk to my experimentalist friends and say, what if you reduce the error bar? What if you go ahead and measure again, measure better, you can do better. And one question that one might ask is, what is the impact of changing the error bars on each one of my measurements on the final result? And as you're seeing by the animation, the red point has a much more impact on my final radius, this quantity of interest, than the blue point. And that is an important thing to communicate with our experimental friends. I thought I was going to talk about this in detail, but when I put all the slides, I realized I don't have time. But this is the final conclusion of my thesis work. If you're interested in this, we can talk about it. The formalism that we were constructing is a way in where you can try to, in a linear response way, see how fluctuations in your data transfer to the noise on the final quantity that you're interested in. And the important part is at the end of these approximations, you write your error as a function of this coefficient times your errors in the data. So that allows you to see which, depending on which one of these is biggest, which data point is having the biggest impact on your measurement. If you're interested, we can talk about it, but I'm not going to talk in detail about it. Just look at the pre-animation, and we're back to our other pre-animation. Anyways, so I'm sitting here as a theorist thinking, I just need to go and tell my experimental friends, Rahul, you just need to go and make that red point smaller, dude. That's the one that is going to give us the best solution. And then Rahul is like, yeah, it's not that easy. And he's going to tell us why it's not that easy. Go for it. Of course.
Right. Can you hear me?
That's not an actual microphone, it's just for the phone.
Oh,
Clip it on, it doesn't amplify your voice.
You will have to scream.
there you go. Okay, cool. So, as Pablo mentioned, that the experimental error bars also determine like how good your measurement is and how well you constrain your posteriors. And that's a reason it's extremely crucial to quantify your experimental error bars. And it turns out that there are many sloppy ways of doing those and many rigorous ways of doing those. And there's, as with many other things in life, there's always like a trade-off between how precise you want to be, but like at what point you can actually approximate certain things. So my goal for these like 5 to 10 minutes of my talking is not to give you like a rigorous approach, a rigorous statistical approach, but to sort of give you like a practical handle on how you get these uncertainties, so that if you're an experimentalist, you can get a version for how you do experimental error analysis. Or if you're a theorist, you can actually ask your experimental friends that if this was followed or not, and basically get a feel for how it is. So let's start with what we actually measure. So when you're doing experimental measurements and you say like, oh, we are measuring the energy of this gamma ray, it's not the energy of the gamma ray that you're actually measuring. it's the voltage in your, or the current or the charge collected is the actual measurement. And there's some amount of model dependency going from that charge collected or the light collected or n number of things going to your model and saying that, okay, this was the energy or these are the number of counts. And many times, like nowadays, we use electronic digitizers. So whenever like the voltage goes beyond a certain threshold is when you say, oh, I record a hit in my detector. And so this then comes with a fair amount of model dependence where you can actually propagate all those errors, and to do it rigorously would be extremely annoying for anyone. So some of the tricks that we use there is we use like calibrations. For example, you know the energy of a particular gamma ray, and you basically equate that, and then you fit like a one-dimensional polynomial or two-dimensional polynomial, and you do calibration. But those calibration fits, if you do them in a Bayesian way, will have error bars, and in principle, you should propagate those, but the errors in calibration data are fairly small enough that you can treat them constant, which is okay in comparison to the other errors that you'll be getting. The other part is like what I want to highlight is most of your data in experimental nuclear physics at least will look something like this, presented in the form of a histogram, because the things that you're measuring are actually random variables, and what you're doing is getting more and more statistics in any experiment. And so you perform that measurement over and over again and get some kind of a histogram for the quantity of interest. This can be a 1D histogram, 2D histogram, if you're looking at coincidences, whatever. So keep that in mind. A good property of this histogram is whether a particular count goes into which bin actually depends on the binomial distribution. But if you approximate it for like larger, like p goes to 0, the entry in each bin actually comes from a Poisson distribution. And it's a Poisson distribution is characterized by just one number, that's the mean. And the variance is given also by that number. So the standard deviation is the square root of that number. And it's also interesting to note that Poisson distribution can only take on like positive values, which is good because the number of counts in your bin cannot be negative. It's a nice property. And as your lambda becomes large and large, your Poisson distribution starts to approximate Gaussian distribution. So whenever you're looking at a particular bin size, what that means is people will sloppily say like, oh, if I have n counts in my bin, the error is square root of n. Well, it actually comes from this Poisson distribution because the counts do indeed follow this Poisson distribution. Now, for any kind of measurement, you're most likely doing one of the two things. You're either counting the number of counts in a certain region, or you're trying to fit your histogram and extract parameters from this fit. So there are sort of basically like two things that you can do with your data. If you're counting the uncertainty quantification for counting, it's for, as we spoke about, for each bin, your uncertainty is just the square root of n. And so if you're looking at the number of counts in this region, you basically add them, and the errors add in quadrature for additions. And so the total number of the total error on like these counts would be just square root of the total number of counts. So that's okay. But one of the caveat here is if you have some background that needs to be subtracted from your measurement, a lot of the times people just like quote their errors as square root of the actual number of counts that you get after subtraction, but that's wrong because that does not follow Poisson distribution. What follows the Poisson distribution is actually the histograms that you measure in the lab. And so even for n1 minus n2, your error will still be n1 plus n2. And that becomes tricky when you have, when your background is actually like getting closer and closer to the signal, the percent error in your measurement will increase. And that has to be taken into account for your accurate error bar. Next thing you can do is like fit a parameter. So in principle, you should do Bayesian fitting. And you saw like a lot of like the talks on how to do that. You'll have priors for your parameters and you'll have posteriors for your parameters based on this data. But a lot of the times this is like not practical if it becomes very expensive because of like huge data sets. So it's okay to do chi-squared, but then the problem there is that you don't get to propagate those systematic uncertainties. And so for that, a good sort of like a backup thing to do is like if you have a function of a and theta, where theta is your systematics, these are your model parameters which you are not directly learning from the data, whereas a is the parameter that you're learning from the data, you basically sample from theta and then try to fit this curve over and over again, and that will give you a distribution for the parameter a, and that sort of can be your systematic errors, and this can extend to many more parameters as well. And this chi-square assumes that you are following a Gaussian distribution, and as long as the number of counts in your bins are fairly large, like more than 6 or 8, they will follow Gaussian distribution, and chi-square is sort of still okay to do. And yeah, with that, I give back to Pablo.
Thank you so much. I am so not used to think of experimental measurements as scam. I'm so used to think them as a nice point that already has an error bar, and I don't have to think about it.
You can scan it as already. You don't do that.
Oh, I knew that. Thank you, Rahul. And this is going to be, as I have said before, a common theme of the summer school conclusion. If you want to take only one thing home, is that collaborating with folks and doing the projects together and thinking, oh, if I am in an experimental group, we need a statistician, that will probably yield to very good results. The same if you're in a theory. And actually, I have found that there is no limit of people that you can put in a paper. Some people might tell you that is the case, but it's not. So you can always invite them. They're full of solutions, and they're usually very, very happy and friendly people to come and try to help. Anyways, so this was our first problem, a simplification of a lot of things, the explanation by Rahul. Now I want to tell you what will be the next level of experimental design. In this case, this was relatively easy because we had one thing that we were interested in, we had one model, and we had one experiment that we could do. And now we complicated things on the next level. I have my entire nuclear chart, and now all of you are experts on what this is. I am working at effort, so there are many things that I might be interested in learning from all of this nuclear physics. Let's say that I want to focus on astrophysics, and from astrophysics, I want to focus on the R process. The R process is a rapid neutron capture process. When you have, for example, two neutron stars that are colliding, you have a bunch of line neutrons, your nuclei are going to start absorbing all those neutrons really, really fast. To model that is extremely hard. You need to have information on a lot of properties. We talk about many of these properties on the nuclei. Let me focus on the masses, the binding energy. And for those masses, you may have a lot of models that you want to use to predict what are the masses of your nuclei. And let me focus on 2 of those models. And if I grab 2 of those models and I compute the abundances, this is telling you the 2 stars collide, how much of stuff you have. As I change this stuff, that is what is sitting in here, I get already predictions and bands that are different. Not horribly different, but appreciably different. That means that which model I'm using makes a difference. So you take all these things into account and you say, okay, let's do experimental design. Aha, I have a lot of experiments that I could do. Not only that, in principle, reaching very far away from stability, very far away from these black and blue colors on the colors when they start turning red, making these nuclei is very, very hard. So the type of experiment will also matter depending on the count rate that you have. And once you have all these, you need to factor into account the fact that we only not have this data in the lab. We might have data from observations like the neutron star gravitational wave signals, or the things that some telescopes are trying to measure on the properties of neutron stars. So you put all these things together, and now it's not so easy. It's actually really complicated. And I'm not the only person saying these things, and there are papers trying to address how much the uncertainty that we have in our nuclear models actually propagate to any predictions that we're trying to do with this. So let's look at a paragon of experimental design. And I was asking ChatGPT what words I could use to describe a paragon of experimental design, and she came with a paragon. I didn't know what that word meant, and this is the explanation, so I wanted to give credit, and that's what we're going to call it. You have your function J. And in this function J, my utility function, I'm going to make this series. We're going, so buckle up. We are going like serious experimental design. I'm going to make this function depend on all of these things, all possible measurements and errors. I go back to my nuclear chart and I say, I can measure everywhere in here with some errors. All the data that already exists. I have all these available masses in this case, but I could be putting all the other data that I made. All the reasonable models that I could come up with. You can go to the BMEX webpage that Kyle might talk a little bit about that tomorrow, or this will mention it. here's a list of many models that I could use for the masses. And all the quantities that I'm interested in, let's say lifetime, masses, and capture rates. I'm going to put all of these things, and my J is going to depend on all of those, and I don't know what's happening with the animation. Once you do that, you say, easy peasy. My new location, the new nuclei that I need to go and measure, that's what I want. And the errors that I need to aim for example, the mean time that I'm going to allocate for that, is just given by the arg mean of this integral. Yeah, easy peasy. Let's break it down, otherwise it will be super hard. By the way, this is very similar notations and ideas from this paper by some of our collaborators, Jordan Melendez, Dick Fronstall, and people that are also from the bank collaboration. So if you want to see these applied to other things or in more detail than just a presentation, I strongly recommend that you go and check on this paper. So let's break this down. I have in here my integral, I have J. Is the utility function that depends on all of these things. For example, in the case that we were playing before, my J was the uncertainty in the radius. That could be the radius of my lead numbers. Then in here, my quantities of interest that I have no idea how I'm going to weight them. I need to do something with them to construct a number, so that's a problem. But let's just put it in there. I have my quantity of interest Q, and I have my Bayesian posterior on Q given the new observation that I'm making. This is Y new that is in here. So, for example, in here, the quantity of interest was the radius, and the observation was the location of the red point that I was checking on the parameters. Then all the reasonable models with uncertainties, I am using this notation. I'm saying my quantity of interest depends on my parameter model alpha, but also depend on all the possible parameters, all the possible models that I could have, and on the hyperparameters that I'm using to mix them. Alexander talked a little bit about it. You could mix them in different ways. So I'm just going to put all of that information in there, and I'm going to integrate over that as well, because I am not sure what is the perfect way of mixing these things. And as Frederick, I wish he would have said exactly this, but I'm going to just put him because that's what I have understood from my conversation with him. Everything that you're not sure, you need to take into account, and you need to integrate over with an appropriate distribution. Finally, these new Y new in here are the possible measurements and errors that we can have. And very important, when I was showing all the plots that I was showing you, I had a green curve, as if I already knew the answer, I already knew the truth. But if I already know the form factor, why am I measuring this? Back then, what I was doing, I was using some expectation of what I think the result of the experimental measurement could be. But in principle, I'm not sure about this. So if you already know what we need to do with things that we're not sure, we need to take that into account, and we need to integrate over. And that's why all of this integral that you're going to do once for one value of the possible experimental outcome, outside of that, you need to integrate again over all the possible outcomes that you could have come out of experiments within the reasonable models that we have. By the way, a parenthesis on the importance of mock data that is very related to this. Let me give you this example. I think you're going to like it. Suppose, I don't know if you have had a friend like this, but suppose you have somebody that comes and tells you, I can predict the stock market from looking at the clouds of the day before. So I look at the clouds today in the afternoon, I can predict what is going to, the stock market is going to look tomorrow. How do you prove this person wrong? What will you do?
Well, you look at the data for the number of times that Nicolas Cage has been divorced, and then you correlate those things.
Very good, but with the clouds.
With the correlate with the clouds first.
You correlate the three things. Okay, very smart.
Yeah.
One different way I'm going to propose that doesn't involve Nicolas Cage is you lock them in a cell. It's very non-human friendly, but you lock them in a cell.
Well, if they're using clouds to predict the stock market, they need to go.
Well, I'm not sure. That's the point. Maybe they're right. That's the experiment we're doing. So we're going to lock them all day today and all day tomorrow. I'm going to take pictures of the clouds and I'm going to show it to them. And then I'm going to ask them to predict what is going to be the stock market without having any information. And I'm going to compare what they predicted with the actual thing that happened in the stock market. And I'm going to do that a couple of times. I'm going to say, you're crazy. You are claiming something that you're not able to do. And that's the easiest way to say something doesn't work.
Is that a picture of Saskatchewan, Manitoba, North Dakota? Where is it?
I have no idea, the internet. So here's the thing. That is the power of mock data. If you have somebody that comes and tells you, oh, my artificial intelligence model can extrapolate any model on any data set, or my statistics method can recover data very precisely from the experiment, or I can read tea leaves and read the future very precisely, what are you going to tell them? Have you tried mock data already? That's the reaction that I want to be engraved in your heart. Is If you prove that your thing works in mock data, that doesn't prove that it works in the real experiment. But if you try the mock data and it already doesn't work and it's given nonsense, I don't have too much confidence on applying this thing to the real thing. Basically, that is the idea of integrating over this Y, is to try to get a sense on that. And Kyle is going to talk about that when he's going to mention a couple of things when he talks tomorrow about emulators, especially in the extrapolation part. So we're back to this. I'm putting all of the things that I want in here. We have my utility function, the interest, the model parameters, the mixing parameters, the possible outcomes, and that's it. I just need to find the minimum of these integrals with respect to where I put my measurements. Let's make an example of how long this will take. Suppose that in this case, I want to estimate the next 10 masses that f should measure. Okay, so Q is my abundance pattern. That is what I'm interested in. J is the uncertainty in the abundance. Let's try to minimize that. I have, let's say, 5 models. I have 2,000 measured nuclei. I have 500 possible nuclei that I can look at. And let's assume that I have very powerful computers and each mass model takes 1 minute to predict the masses of all those, or a single nuclei. I think I made it a single nuclei, which is, no, that is not true. It usually takes way longer. Let's say that each abundance calculation takes around a day. That is a very expensive calculation. Let's say that every integral of every quantity that you see in here, I am so good at quadrature rules that I can get that integral with 100 evaluations. I don't need to evaluate in a very fine grid. That's how good I am. And let's say that once we're doing all these things, this depends on x, I can get to the minimum of these functions in 500 evaluations. That's how good my, I guess, Jacobian estimation is. Like, I am really good at minimizing stuff. If you put the time that all of these will take, you have your time budget, you make your multiplications, and maybe I didn't mess up anywhere, you get something of 10 to the 14 seconds. To put a perspective, 10 to the 14 seconds is around 1,000th of the age of the universe, is comparable to the half-life of uranium-235, is around the time that it requires a supercomputer to tell you that the answer to everything is 42. And not only that, in that time, you could go, if the time is the only problem, you build 1 million metrics, one after the other in sequence, and you measure every nuclei that we wanted to measure 1,000,000 times on each one of the efforts. And that's how long it took you then to do the experimental design in an optimal way. Just curious, out of curiosity, I was thinking, how much would it take if I just grab all the computers in the world? It's amazing, it would take us 2 days. If you could grab all the computers power on the entire world, you just finish this problem in 2 days. Which is tells you something interesting about the computational power that we have. So I hope that I have with this convinced you that what I'm saying is doing any of this is completely and utterly impossible. You just cannot do it. And Kyle came up with a very nice phrase to answer this, is that nothing is impossible through the power of friendship. And this sounds like I'm just talking BS, as Frederick said, but no, I am serious. And that's why you need a lot of friends and approximations. I'm going to talk about the approximations, those are important. But that's why you need to tackle these type of problems in groups, so that other people might come up with ways of approximating something here and there, so that at the end you can get a meaningful answer. And these are nice pictures of many of the collaborators that we're putting together, including you. Some of you are here, and I want to put another picture of what I did today. So, a couple of approximations, and then we go to the hands-on sessions. One thing that you could say is, screw it, I'm not going to put any Y new dependence. When we did the maximum variability, see that I was not taking into account what is the outcome of the experiment. I was just saying, model, where are you most uncertain? And that was it. And that makes everything faster. You could ask for linear responses and say, you know what, just trying to understand how my model behaves linearly around its best value, maybe I can just get away with that. That's part of the transfer function thing that I was talking, not exactly that, but it's very similar. That is an approximation that you could make. You could say, nah, I'm just going to take into account one model, I'm not going to mix them, that is very expensive. Or I'm going to do it in such a way that I'm not calibrating and mixing at the same time, so that I can separate these integrals. And finally, you can apply dimensionality reduction to many things, both your models, and we're going to talk, Edgar is going to talk about that tomorrow in the modular reduction part, to your outputs. Kyle is going to talk about, to focus on that on the practical emulation part, or you can apply those for posteriors themselves to try to understand how your probability distributions can be described maybe in a lower dimensional space, such that you don't have to do all these integrals in a complicated way. And that is what is going to be the focus of tomorrow. And now you know why, this is a very nice close, why tomorrow is tomorrow, why we're going to focus an entire day on trying to get these type of approximations to work. Having said that, we're going to go to the hands-on session time. I think I didn't went overboard. We're going to follow the same protocol. I'm going to show you the 3 or 4 examples that we have. And then, my friends, it's up to you. You need to figure out this yourself. So these are the challenges that we have put with Rahul. I'm going to go through them. And this was always an option. I'm just going to highlight it. I have no idea how hard this is going to be.
Oh, that's a map of another, that's a US state right there, those stars. You know which state? Yeah.
Florida.
Florida!
Yay! Yeah, I put it because of Tallahassee. No, for real. You can start working on your own thing. And you know, you could make this your final project. Wouldn't that be nice? That way I can buy a box of alfajores just for myself. So the first problem is you're going to follow the problem that I was doing in 2016. There is a paper to guide you. I put some guidance and ideas on the notebook. So the idea from this is select where to measure the second momentum transfer for lead 208. And then you can play saying, what if I want to measure 3 times, 4 times? Try to find a way to figure out where you need to put those points. And what will happen if you change the variability of your points? That is all the associated error. That is also an option. You can buckle up and go to the paper that we published 5 years later, in where we consider not only lead but calcium, and you can try to play the same game in there with the machinery that we described on that paper. And if you want to learn about that, I will be more than happy to help. Second example from what you already learned on the morning is the calibration of the liquid drop model. In that example, if you already finished, if you didn't, that's completely okay, of course. When you calibrated the liquid drop model, or didn't, if you haven't finished, you use all 2000 nuclei available. What will happen if you can only use 10 or 15 or 5? What will be the most informative nuclei to reduce your uncertainties in the posterior the most? So you need to build your own optimal function. What is the name? Utility function. I have for the last 2 weeks, I having trouble remembering the name of that thing. I don't know why. Anyways, you need to build your own utility function and try to figure out. And it's a nice exercise. If you could go back in time, like, I don't know, 100 years ago, you could tell the people, you only need to measure these 10 nuclei. You don't need to measure the entire chart, and you get a very nice liquid drop off.
Can I give you a mnemonic to remember the utility function?
Yes.
So, you know, when you're standing around and there's like folks who are trying to get through the door, just hold the door for them and make yourself useful. Utility.
Yes. I'm standing here, so I am not smart with questions. I'm sorry, Freddie. Third challenge. Basically the same thing, but for the proton pulse. Try to estimate where you need to put points such that you can measure the proton radius with the smallest uncertainty possible. And turns out, if you go to this paper, you can see that with 15 points well located, you get the same uncertainty level as if you were to put 31 points equidistant. So it's interesting to know that experimental design can actually save you a lot of money. And the final challenge, Rahul will help me to explain, to guide you through this, but basically it's the closest thing that we could give you for an afternoon to feel like you're actually selecting the new masses to measure in effort. And what you're going to do is you're going to grab a lot of tables of mass models that Rahul has put together. This is a picture that I stole from somebody a long time ago. I don't remember the paper where I found this, but this is showing how many nuclear mass models really agree on the location where we have data. And as soon as you try to extrapolate, they start giving you crazy stuff. So maybe a good idea will be, okay, I'm going to measure where the variability is the most. But where the variability is the most likely is the further away possible that is already hitting the drip lines. That is really hard to take into account to measure from the experimental point of view. There is a trade-off between the two. So Rahul has put a function to take into account how much expected error we will have at FRIP, so that you can actually find a place where the variability is the most compared to that precision and make a sensible choice for the next 5 or 10 nuclei solution. Rahul, do you want to say something about this? I already said everything, or yeah. Okay, very good. And that is all. Thank you so much. Go for it, and we will finish at 5 p.m.